Welcome back. Let's resume talking about the derivative. We went through the definition of the derivative using three different notation. This AB notation, slope of secant line, the delta notation, again slope of secant line, and then dy dx. And finally, my favorite Newton quotient notation, which is the same as the AB notation if you do some substitution. And then change this A value around, then you're going to get a function given by the derivative. It is called the derivative function. And then we can actually calculate the derivative function using Newton quotient, but we're going to postpone that. We talked about this theorem. If the derivative exists, then the function must be continuous. So, equivalently speaking, if you have discontinuity, then derivative does not exist. And use that to answer this question. We have some graph like this, and then find out the x-coordinate values at which the derivative does not exist. Immediately we see 2 points, x equal to -4 and x equal to 0. Discontinuity, so no hope of any derivative here or there. There's one more point right here. This kind of point is called cusp, where the left-hand side and right-hand side slopes are different, so we do not have this smooth joining. And at this point, cusp is a good explanation. Of course, we're going to actually do precise computation a bit later. Next question, find the precise value of the derivative f prime of 1. So x equals 1 is right here, so we are talking about the slope of tangent line around here, but this is a line segment. So I don't really have to do anything, just find out this slope of this line segment itself, because this is itself a tangent line. So what is it? Rise over run is going to be -4/3. Next, find out the precise value of the derivative f prime of -2. It's right here, x equal to -2. I hope everybody sees that this point has horizontal tangent. So what is slope of a horizontal line? It should be 0. Okay, the fourth one, I originally de-emphasized, but I'm changing my mind. Let me just include this problem as normal problem. Estimate the derivative value f prime of 4. So right here, and then you have to estimate it. And you'll have to get a rule or something and then try to draw a tangent line, and you have to do some estimation. You don't have to get precise answer because this is estimation anyway. And I did that and I got around 1.5. Of course, it can differ from one person to the other. Try, explore. Now, I left one problem over here. We are going to do something more precise. Yes, indeed we are going to do that. We're going to find the derivatives. This time, instead of asking you to find out the derivative, I asked the problems, same problems, using intimidating limit notation. It is just to intimidate students, nothing more than that. What is this limit? It is the same as the derivative. So from this, I simply wanted to test whether the students remember the definition of the derivative. So this is the same as the derivative, evaluated x equals to 2. So you see what's the definition of the derivative here. This notation, yes, this one. So here it's the same as x equals a equals to 2. So we have to find out the derivative at x equals to 2. Right here, that's on the line segment. So the derivative has to be -4/3. Yeah, -4/3. How about the next problem? We have this h notation. So that's the same as this one, the Newton quotient notation. And then if I compare this with that, a value is -2. So I have to find out the derivative at x equal to -2. It's right here. We already discussed it. It's horizontal tangent, so the derivative has to be 0. Okay, and then let's move on to next two problems, C and D. They are in completely different league. As a matter of fact, I shouldn't have erased that Newton quotient notation, so let me get it back. Okay, and then please recall that this one was actually a slope of a secant line, and then when A is over here, then A plus H will be a little bit to the right hand side if H is positive, a little bit to the left hand side when H is negative. So when we have limit as if H is going to 0 from the positive side, that means the second reference point is coming from the right hand side, isn't it? So this is gonna be right hand side slope at x equals to A at A. Also, when H is approaching to 0 from the negative side, what do you mean by that? A plus H is going to be a little bit less than A, so the second reference point will be on a little bit left hand side of this. So left hand side limit of this Newton quotient means left hand side slope. So if you remember those two, then we can find out these two limits without doing any limit computation. This is the left hand side limit from here. So left hand side, that's a line segment. So that slope is -4/3. -4/3. How about the right hand side limit? That's right hand side slope from here. And that's part of this parabola-like picture. So that slope must be 0 because to the right hand side tangency is actually this horizontal line. So right hand side slope is actually 0. So if you understand what this Newton quotient means, the slope of secant line, then we can answer all these questions by estimating or calculating derivative values precisely, or sometimes estimating from these pictures. Left hand side and right hand side limit of these Newton quotients actually mean left hand side slope and right hand side slope. So once you understand those, this kind of problem is not difficult. I can give you a drastically different picture where we have to do something else, some other line segments or something to get left hand side and right hand side slope, but you should be able to handle that. In order to get really precise answers, you had better get some line segment towards some horizontal tangents, because otherwise you'll have to do estimation. So the variety given by these kind of problems is actually pretty low. So this kind of problems are not difficult at all. Just remember what the definition of the derivative is, and then you can just walk over this kind of problem. Of course, if you do not know the definition of the derivative, well, you will have to pay the price here. You can study all those algebraic manipulations and so on, all those difficult techniques, but you may end up stumbling here in these kind of simple graph problems. And simply by remembering the definition of the derivative, the other students will automatically get full credit and really cashing in these kind of problems. When somehow you are the only one or one of very few number of students who are missing that, that's going to cost you dearly. So manipulating these Newton quotient is one thing. Remembering the Newton quotient is quite another. Everybody should understand it and remember it. About manipulating these Newton quotient, I'm going to leave that to the next segment of the video, and please be warned, the next one is going to be very, very hard.